Ooh, 3 people. Okay. Lydia, Sasha, and Julianne. Okay. Let's see. Okay. 1, 2, 3. 5 more.
For us to get on that Zoom thing, do we just go through Blackboard and?
Mm-hmm.
Okay.
Yeah, there's a
link.
link on the left-hand side. Just go down and say Zoom. Click into it. Okay, let me get back to me. There we go. So now I can position. There we go. That covers everything. All right. Well, by my watch, it's 12:30. And that's when we start. Okay. So. Chapter 7. Thank you. Yep. There we go. Okay. Oh, Nate's here. Well, that sets a record for the most people I've had on Zoom at one time. Does everybody hear me?
Yep.
Okay, good. Let's see, we're missing 1, 2, 3, 4. But it's time to start. So, particular problems before I start rambling. You want me to start talking? Okay. How about, as a matter of review, the electromagnetic spectrum. Let's see, this is going to be in terms of wavelength. So the wavelengths get small down here and long up here. So this far end is going to be radio waves. And the short wavelength is going to be gamma rays. And in between, we go through the whole spectrum. And the visible part is tiny. It's between 400 and 700 nanometers. So you're saying to yourself, what's a nanometer? A nanometer is 10 to the minus 9 meters. 10 to the minus 9 meters is equal to a nanometer. So if you run into a problem that gives you a value for wavelength in terms of nanometers, say, let's just say, just pick a random number. Huh? No. Oh, you made a joke. 560 nanometers. And for all the formulas that you use, the standard value, the standard units have to be used, meters. So this would just be times 10 to the minus 9 meters. And you can plug that number in. So what are some other places on the electromagnetic spectrum? If we go, this end is going to be red, this end is going to be blue, right? Actually, violet. So this one's going to be ultraviolet, right there. And this side's going to be infrared. Okay? Let's see, do I have that spectrum in here? I don't think I do. I shouldn't have. That's something that you need to know. Infrared, then microwave, infrared, microwave, and radio wave. And on this side, we have ultraviolet, X-ray. I feel like I'm leaving one out. Help from the audience. I know there's more in there.
Ultraviolet, X-ray.
That's it? Ultraviolet, X-ray, gamma rays. Infrared, microwave, radio? Okay, got them all. So as the wavelength increases, we go from this to this, but the relationship between wavelength and frequency is wavelength times frequency is equal to the speed of light. Right? The speed of light is constant. So that means you have a product of two variables, which means they are inversely related. So as this one goes up, that one goes down. This one gets smaller, that one goes bigger. So down here, we actually will do the arrow the other direction for frequency. Okay. Now, how about, while we're here, how about energy? What's the energy content of a photon for each one of them? Actually, it increases in this direction. So gamma rays are the very highest energy photons. Radio are the very lowest energy photons. And they're related by Planck's constant times nu, the Greek letter nu, which stands for frequency. Frequency is going to be the units of measure. I should do that. Okay, this is going to be in meters, and this is going to be in reciprocal seconds, or 1 divided by seconds. That's so that the speed of light is in meters per second. Okay. This also is hertz. Somebody thought they ought to honor the German Hertz, who was had a large role to play in electromagnetic radiations. So they gave him the honors, but if you're going to do calculations, reciprocal seconds is the way to go. This one, energy is in joules. Frequency is still in reciprocal seconds. So Planck's constant is going to be in joules per second, so that the seconds cancel and leave you with joules. And that value you'll be given. Right? It's in useful information. In the back of your review document, it'll be there in the exam also. But that way, as this number gets bigger, which is to the left, energy gets bigger also. Now, what if you're given wavelengths and you're not given frequency? Well, you have two options. You can just go in and plug in 2.9979 times 10 to the 8th meters per second for speed of light, and plug in the wavelength in meters and solve for frequency, and then use that frequency value in here. Or we can solve this one for frequency, which would be C divided by lambda. I just put lambda over here on this side. So then you can plug this value, the equivalence of that, into here, and that's H times C divided by lambda. And then you can do, if you're given lambda, then you can do the whole thing in one calculation. Okay. Let's see, what's next? We have several problems that we could do. I'm just kind of hitting the high points right now. Concepts. Okay. So that is a synopsis of electromagnetic radiation and its characterizing numbers, plus how much energy is contained in a photon. Next, we can talk about where do those photons get their energy? Well, as far as chemistry is concerned, photons get their energies from transitions of electrons in atomic orbitals. So if we have a nucleus, then we'll have an orbital here, and the second one will be here, and the third one will be there, and the fourth one will be there. And they get closer and closer together as you get higher. The light that you see, or the light that you measure, comes from a transition from an electron from one outer orbital to an inner orbital. Right? The closer you get to the nucleus, the lower the energy of the electron. So if you go from a high energy to a low energy, it's got to give that energy up somehow. Where does the energy go? The energy goes into light. So say if we were to just do something simple like going, this electron jump from 2 to 1, then it's going to give off energy in the form of a photon of light. Or if we say we have an electron here and a photon of light comes in and strikes it, it will be promoted to another orbital, say they go out here. So it took that much energy to go. And as a consequence of this model, which is the Bohr model, the movement of the electron from one level to the other is quantized. That means the amount of energy is in packets, and you can't have more, you can't have less until you get to the next quantum. So what do I mean by that? Well, what I mean is, if this radiation comes in here and strikes that electron, and it has less than the amount of energy required to go from here to here, it won't move. It'll just be converted into heat. If it has more than the energy it needs, then it could go to here, or it could go to there if it's got enough, or to there if it's got more. But it's going to use the amount of energy it takes to get here and then the extra becomes heat. But the transitions from here, from between levels, will give you an exact wavelength or frequency, amount of energy. And we can calculate those. We just need, and that the formula to do that calculation is in your useful information, about 2/3 of the way down in the middle of the page. Okay, that's our starting point. In fact, this tells you the amount of energy that's contained, the energy level at which the electron sits if it's in one of these orbitals, 1, 2, 3, 4 on up. The Z is the same as at the very beginning when I gave you the symbols. Z is here, A is there, charge is there, and number of them is there. So this Z is the atomic number. Right? So you plug the atomic number in here with one caveat. This formula only works for atoms that are hydrogen-like. That means they only have one electron. So, of course, if it's hydrogen, it's like that. If it's helium, it has to be an ion, one electron. Lithium, it's got to be this, and beryllium, it's got to be this, so forth and so on. Then you can use that formula. Otherwise, you can't do it. So if this is the energy at each level, then the energy of a transition or delta E is final minus initial. Right? So if it starts at if it starts out here somewhere and goes to here, then you put in the initial starting position here and the final, whatever it is here. So let's do an example of that. And we'll just stick to hydrogen. So let's say we get a transition from a 2 to a 1. N equals 2 to N equals 1. So the final position is 1. Minus 2.178 times 10 to the minus 18. Yeah, it's recording. Times, of course, this is hydrogen, so Z is 1 squared. And the final is N equals 1. Okay, that's easy enough. Then we subtract a minus times a minus. And this is 2.178 times 10 to the minus 18. And that one is times 1 squared over 2 squared. Because this is the initial starting position, 2. All right? So, what is this equal to? Well, that's 1 over 1. So it's minus 2.178 times 10 to the minus 18. And this is a plus, right? Minus times a minus, plus 2.178 times 10 to the minus 18 times 1/4, right? 1 squared over 2 squared. So if we say, we're going to simplify this. There we go. So now this is, if we can factor out that value, and then on the inside we get a -1 from here, and we get a +1/4 here, then this value is -3/4, right, times a positive. So whatever -3/4, 0.75 times that value. Let's do that. .178. Oops. So that gives us a -1.63 times 10 to the -18 joules for the transition from here to here. Now, notice the sign convention. By doing this operation, we ended up with a negative. And it's just like thermochemistry. Everything's related to the system. Here's the system. And if we get a jump from here to here, then the system's going to lose energy. In this case, it's going to lose energy as a photon, right? So any negative energy means that we've lost energy from the system and we're producing a light, a photon. Comic relief. If we were to do this same calculation from here to here, that means this number would be positive, and that means it would have to absorb a photon to get that transition. So, in the slideshow, in the PowerPoints, the delta E was given with these two combined in one. But this is where it came from. That's the only reason I wanted to show you all this, because that shows you how we ended up with that equation from this. But this is the way it's given to you in your useful information, which means you can use this, and all you have to do is say final position minus initial position. And define which one of those is which. Then you can use that, and the sky's the limit. Okay, any questions? Okay. We can work on some specific problems now, if you want. Like we have a couple more concepts that were covered. Let's see. Well, actually, the periodic table, we got to do all of that. Oh, electronic configurations. Right. How to write out the electronic configurations for an element. So, in your useful information, you've got that diagonal chart that tells you the order of filling of your electrons. And you can reconstruct it really easy. Oops. It's 4. B, F, 5D, 5F, 6D. That's about all we're going to need. And then you just draw your diagonals like that, 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 there, And that's how you fill it. 1s comes first, then 2s, then 2p, 3s, 3p. Then you go down to 4s before you get back to 3d. Then 4p, 5s, then back to 4d, 5p, 6s. That's the order of filling. Now, if you know the way your periodic table is set up, you can deduce all of that from the periodic table. So I'm going to switch, I'm going to rotate over here a little bit. There we go. Notice that as we go from element to element, this period is 1, 2, 3, 4, 5, 6, 7. And that's good for these 2 columns and these 6 columns. These will all be 1s, 2s, 3s, 2p, 3p, 4s, 4p. But when you get into the transition elements, you have to back up, just like we did here. Go down here, you have to back up here. So this is going to be 3Ds here. This will be 4Ds, whereas this will be 5s and this will be 5p. Okay, that's the way the table's built. And as you fill your orbitals, you can go 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 3, 4, 5, 6. And you can go 3s1, 3s2, 3p1, 2, 3, 4, 5, and 6. And then you go to 4s1, 4s2, then 3d1, 3d2, 3d4, 1, 2, 3. Then we have a discrepancy here and here that I'll have to explain. Okay, so let's do an example first. How about let's pick one out of the how about problem okay, 44 is 10. We got 10, and we need to build that atom. Okay, we look here and find 10, it's right there, and 50 is the atomic number. That means the neutral atom will have 50 protons and 50 electrons. So now we start filling it. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 3p, 4s, 4p, 5s, 4d, 5p. We'll see if we need, we may not need all of those. But notice how I found those. I went to 3p, and then at 3p, I had to go back to 4s before I get to 3d, and then 4p, and I went to 5s, 4d. That's why I did it in that order. This is in order of energy. So, S's can only hold 2. P's can hold 6. So there's 2 more there, 6 there, 2 there. D's can hold 10. Well, let's see how many we've got. There's 10, and there's 10 more, there's 30. So we've got 20 more electrons to go. So that's 6, 7, 8, 18, and then 2 makes 20. So that's the complete electronic configuration for 10. Okay. If the problem asks you for the complete electronic configuration, you give them that. If you're allowed to use an abbreviated, or the abbreviated form, then you go from 10 and you go backwards until you get to your nearest noble gas. In this case, krypton. Krypton 36. Then you go here and start filling these. So that's 1, 2, 3, 4, 5. 5s, 4d. And then 5p, 1, 2. Okay, that's your abbreviated form. I see Cody's name, but I don't see Cody. Are you there, Cody? Okay, just checking. So I'm missing Tyler and Destiny. They're not there. Any questions for electronic configuration? Okay, what happens if we 10, I think one of the possible charges on 10 is 2 plus. Let me check to be sure. Yeah, it'd be 2 plus or 4 plus. So let's say we have this one. How would you write the electronic configuration for that? Well, you get there by taking the highest energy electrons away until you find that balance. So this would be and we would normally have those two, but they go out. So that would be your configuration for that ion. We had to lose 2 electrons to give us an imbalance of 2 positive charges. Okay? That wasn't part of the problem, but I just thought I'd make that point. You guys are going to have to chime in with questions because I've only got 3 people here in class. How about, let's look at the quantum numbers. Be sure we have those in line. There's the principal. This is the, God, why do I do that? I start down that road and then I forget. Here we go. Angular. This is the angular momentum quantum number. This is the principal quantum number. This is the magnetic. And then you have spin. Those 4 numbers completely describe the electronic structure of an atom. This one refers to the energy. That's why we can use N in our calculations of energy. That's what it's for. Angular momentum refers to size and shape of the orbital. So s orbitals are spherical. P orbitals are kind of dumbbell shaped. Magnetic refers to orientation. What direction is it pointing? Right. For spherical, you don't have a direction. Right? The direction is 0. For p orbitals, the direction could be either x-axis, y-axis, or z-axis. And the spin is just spin. It can either be plus 1/2 or minus 1/2. That's the easiest one. So n can be any number from 1 on up in whole number increments. L can be any subset. Remember, for those of you who weren't here for the lecture, lost my train of thought. Oh, it's like a tree, branching tree. So you can start here and it'll branch out. Or you can start here and branch out, start here and it'll branch out. So each one of these is a sub-level of one of those. So for this one, you can have the total number here equals the value of n. And they can be from 0 on up to n minus 1. So if we are sub-leveling 4, it can be 0, 1, 2, or 3. That's 4 numbers. The magnetic takes one of these. Let's say we have a 1. We're at L equals 1, right? So if L equals 1, it can be minus 1, 0, or plus 1. You just take the number, go to the negative, work your way up to the positive by whole numbers. And spin is just plus 1/2, minus 1/2. Okay, so let's say we're at n equals 4. What's the maximum number of orbitals you can have at n equals 4? Right? If n equals 4, then L can be what? Zero, 1, 2, or 3, right? All right. So there's 4 levels. Now we're going to subdivide these. 0 can only have, okay, so these are L's. These are M sub L's. Right? So that one can only be 0, right? Because minus 0 is as far as you can go. This one can be minus 1, 0, plus 1. This one can be minus 2, minus 1, 0, plus 1, plus 2. This one can be minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. Okay? And spin is not a level. Spin is characteristic of the individual electron within the orbital. So when we say how many possible orbitals can you have, we stop here at M sub L. So at n equals 4, we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 at level 4. Okay, convention. I've already used the convention for electronic structure, SPDF. SPDF refers to angular momentum. So these are the possible L's that we're going to discuss. You can go higher than that, but these are the only ones that are important to us. 0 is given an S, 1 is given a P, 2 is given a D, and 3 is given an F. So when you write your N numbers, you can have 1s, that's as high as you can go because there's only zeros. But 2 could have s's and p's. So it could be 2s or 2p. 3 could have 2s, 2p, 3s, 3p, 3d. And 4s can have s, p, d's, and f's. Okay, that all translates into the periodic table as well. If you think about, once you get down to this level, let's see. Right, so that each one of these can have a sub-level. This one can only have 1. This one can have -1, 0, +1. So that's 3 levels. D, let's put D over here. D can have -2, -1, 0, 1, and 2. So D can have 5 levels. And F can have 7 levels, right here. So F can have 7 levels. Now, to each one of those levels, you can have 2 spins. That means 2 electrons, right? So S can only have 2 electrons, maximum. P's can have, at 3 levels, 2 each, can have 6 electrons. D's, since they have 5 levels, they can have 10 electrons. And F's, since they have 7 levels, they can have 14. Okay? Now, if we go back over to the periodic table, we see that it translates. S's are here. S can have 2 electrons, 1, 2. D's can have 6, 1, 2, 3, 4, 5, 6. P's, excuse me, P's, SP. D's can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And F's, guess where F's are? Down here. 14. That explains why the elements are grouped the way they are and why you have that many numbers at each level. Okay. That's a lot of information to take in. If this is the first time you've seen it, if you've had a chance to review the video, then this won't be the first time you've seen it. But it still may be a lot to take in. Okay. Trends. Periodic trends on the table. We talked about 3 trends. Ionization energy, electron affinity, and atomic radius. Okay? Ionization energy, you need to know how it's defined. Ionization energy is the amount of energy you put into an element in its gaseous state. You do that again. And non-ionized, you put energy into it and you get the release of 1 electron. Okay, it has to be a gas, both here and here, because we don't want any other complications to enter in. If it were a liquid or a solid, you would have interactions, significant interactions between the atoms within that state. Whereas with a gas, all the elements are virtually independent of one another. So any energy we put in affects only what we want it to affect, and that is the electron. For electron affinity, we start with the same non-ionized element in the gaseous state, and then we measure how strongly it attracts an electron. So it gives us a negative ion. Okay? So remember the convention. The amount of energy we put in, if we put in, since energy is going into the atom to expel the electron, then the higher the ionization energy is more positive, right? Because it's going into the atom. Whereas electron affinity is measured as a negative. Because as the electron comes in and attaches itself to the atom, its energy is decreasing. The closer you get to the nucleus, the energy of the electron is decreasing. So we measure that amount of energy, and the more affinity an element has for an electron, the larger the negative value for it. Okay? And atomic radius is just, it's usually, I'm trying to think of the units of measure. Not nanometers, picometers. It's usually in picometers. So what's a picometer? 10 to the minus 12th meter is a picometer. So it's 1,000 times smaller than a nanometer. Okay, now for trends. I'm gonna leave those up there. The periodic trends in the table are best described in terms of representative elements only. That is, these guys right here and these. When you get in here, it gets a little more complicated. It's like a roller coaster ride. The trends are not as well understood or behave as well. So, for ionization energy, as you go down in a group, it takes less energy to expel that first electron. Or as you go up, it takes more energy to expel the first electron. As you go left to right, it takes more energy to expel the electron. So as a trend over the entire table, from lower left to upper right, ionization energy increases. Let me just say, periodic table, that direction, increase. Okay? Electron affinity. So as you go down, electron affinity becomes weaker. Or as you go up, electron affinity becomes stronger. Now, in terms of numbers, the strength of that affinity means a more negative number, right? So as the affinity gets stronger, the number gets negative, more negative, based on what I just described for that value. The electron affinity for periods, from left to right, the affinity increases, which means the number becomes more negative. So let me be consistent here. So if the ionization energy increases, that becomes more positive. Whereas electron affinity, you get a similar trend. You increase the affinity, but that means the number becomes more negative. Okay? Now for atomic radius, as you move down a group, the atomic radius increases. And as you move from left to right, the atomic radius decreases. So from right to left, the atomic radius increases. So for atomic radius, we get just the opposite trend. We increase radius from upper right to lower left. Now, why does that happen? Why do these things happen? Okay? Let's go back to ionization energy. Why does it take more energy to expel an electron as you go up? The reason for that is you're getting closer to the nucleus. In other words, you're trying to expel an electron from a smaller principal quantum number, right? And remember, the lower the energy, the smaller the n number, the lower the energy. So in order to go from 1, for instance, to infinity, which is ionization, takes more energy than it does to go from 2 to infinity. That's why ionization energy increases as you go up. Ionization energy from left to right increases because of effective nuclear charge. That is, you're getting more protons. You're still at the same energy level. N is the same, but you're adding more protons, which means a stronger pull on the electrons. So that explains ionization energy. How about electron affinity? Okay. Actually, they're very similar. As you go from left to right, you're increasing the number of protons at the same energy level, which means the attraction for electron is much stronger. Right? So its affinity is going to be greater. And as you go down a family, the effective nuclear charge, you're adding more protons, but you're also adding more electrons, which tends to shield the inner electrons, the core electrons, shield the nucleus from the outer electrons, which makes the pull much weaker. So the infinity becomes weaker this way, stronger that way. How about atomic radius? Atomic radius increases as you go from top to bottom. That's because you're adding energy levels. Right? You're going from 1, 2, 3, 4, and those mean you're farther away from the nucleus. You got a bigger atom. How about left to right, though? Well, if you go from left to right, you're adding more protons at the same energy level. Right? And what they're doing is they're pulling on those electrons stronger and stronger from left to right, which shrinks the electron cloud around the atom, and that shrinks the size of the atom. So it shrinks from left to right, and it shrinks from bottom to top, which means the trend for getting bigger goes upper right to lower left. Okay. Now, as it turns out, we have a buffer day. In fact, this is a buffer day. So I'm doing a review today, but come Wednesday, you have an opportunity to, I'm going to expect questions on Wednesday because I don't want to have to do this all over again. And let's see, let me check my things here. I know that's true. How about lab? I don't think we have a lab until next week. Right, on the 10th. The lab we're going to have on the 10th is determining the molecular weight of an acid by titration. So come prepared. Let's see what other trouble we can get into. Ionization energy. The trends we were talking about with ionization energy were for first ionization energy. that is the first electron. For instance, let's just take an example, magnesium. All right? So magnesium, and this is another opportunity to describe. I almost had a new student. A little short, but we'll take what we can get. The discussion of core electrons versus valence electrons. Valence electrons are, in a nutshell, are those electrons that are available for bonding. So for ionic bonding, those are the ones that you kick out and give you your ion. For covalent bonding, those are the electrons that participate in sharing with other atoms. And how do you tell which ones you got? Well, you start with, you take your magnesium, for instance, you work your way backwards until you get to your nearest noble gas. And you say, all right, how many steps did I have to take? Well, to get from magnesium to neon, you took 2 steps. That means 2 electrons are available for bonding. The other way, magnesium is in the alkaline earths section. Second column, it has 2 electrons that are valence. So we've got 12 protons total, means 12 electrons. That means we have 2 electrons are valence and 10 electrons are core. Okay, so that's important for ionization energy, because that was where I started with this discussion. So you have an ionization energy. The first ionization energy for magnesium will be some value, whatever that happens to be. And then the second ionization energy will be greater than that. It'll be an increase in ionization energy. Why? Because to get to this point, you're producing that one. To get to this point, you're making that one. That first electron is removed from a neutral atom. Right? So there's a certain amount of pull, but once you get to +1, then take that second electron, it's got to pull not only away from the magnesium atom core, but it's also produced another positive charge that it has to overcome. So the energy increases from here to here. Now, when you go to this level, you've got a huge increase. Why? Because you've already taken away the 2 valence electrons. Now you're into the core. And core electrons are very stubborn. As a rule of thumb, you'll go from here to here, will be 10 times as much energy. That varies, but as a general rule, it takes that much more. So that's the rule. Anytime you finished with your valence electrons, the next time you get into the core, you see a huge jump in energy to remove that core electron. The other explanation for that is you're getting into a noble gas electronic configuration, which is that is like neon. They're similar. What's the symbol for that? They're not equal to one another. They're similar to one another. And that means, and neon is a complete electronic structure. That is, it's 1s2, 2s2, 2p6, right? So that's 10. All of these orbitals are full. They're perfectly happy just the way they are. Don't want to give up any electrons. In fact, that's one of the explanations for chemical reactions. Everybody's trying to look like a noble gas. Sometimes they do it by making ions. Sometimes they share electrons and fool themselves into thinking that they're noble gases. Okay. Let's see. All right, there are some, let's see, I wouldn't say discrepancies in the trend for ionization energy. If we move across here from boron, carbon, nitrogen, oxygen, fluorine. Boron, carbon, nitrogen, oxygen, fluorine. So boron is 5, 6, 7 for nitrogen, 8, 9. Then we have 1s2, 2s2, 2p, 2p1. Then all of these are going to be the same, except for these. The 2p2, 2p3, 2p4, and 2p5. Right. Now what we need to do to understand how the ionization energies change from one to the next, right? From left to right, the ionization energy should increase. And it does, but there are some reversals that we have to account for. So remember, P's have 3 orbitals with 2 electrons each, maximum. Right? Okay, there are your 3 orbitals. Sometimes they call them X, Y, and Z. So this one's only got 1. Right? This one's got 2. And remember, when you fill these orbitals, you have to put up spin, for instance, up spin for all 3 of them before you can go back and start putting down spin. You don't pair them up until each one has at least 1 electron. Okay, so that's nitrogen. We've got, I'll put this over here. So now we can go in here and add one like that. And for this one, we can go in and add one like that. Oops, too many. There we go. Now, what are the discrepancies? Well, for this group, you're going to have an increasing ionization energy as you go down from here to here. Right? We've added a proton, so this one's going to be harder to remove than that one. And here, we've added another proton, so that one will be harder to remove than this one. But this one, yeah, this one is easier to remove than that one. And the conventional wisdom is that one is paired with another electron in that orbital, and there's a repulsive effect. So it's easier to remove this one than it is to remove that one. So the ionization energy trend here, as we're going, let's see, we're going up here, we're going up here, we go back down there. Then we start going back up again. So this trend reverses itself right here for that reason, because there is some repulsion. Let's see. Trying to decide how much detail I need to give you today without your heads exploding. And then we can pick it up again on Wednesday. Am I out of time anyway? 1:30? Getting close. 1:33. Any questions? No? Everybody's happy? Okay. Well, if you haven't worked all these problems, go ahead and finish them up, and then Wednesday, hopefully you'll have some questions.
And then the test will be Monday.
Test is scheduled for Monday.
And we have lab next week, not this week.
Right, next week on the 10th. All right. You have a copy? Copy?
I think so.
Okay, I think I handed one out.
You handed them out, I think, on the last test.
There. Here we go. They look like that?
I think so.
With a big blank spot right up here. That's your lab. Okay. All righty then. We're done for the day. You have no.
Okey-doke. Hopefully I'll have my car back by next week.
Okay.
I've got to get an antifreeze leak fixed.
Anybody else? All right. I see Coley, Julianne, Sasha, and Lydia. All right. Pretty soon, everybody's going to be zooming in, and I'm going to be here by myself.
I'll try not to let that happen too often.
Okay. We'll see you in a couple of days.